Assalamualaikum and good morning to everyone. My name is Nurliana Syafina binti Rosli and my metric number is 307803. So today I will present question 2, maximization problem. This statement, Mr. Carter eats two types of cereal, which is cereal A and B. Based on the table given, it already provided the amount of calories, sodium and protein per ounce for each cereal. Also, in the statement already mentioned that Mr. Carter's breakfast should provide at least 480 calories but less than or equal to 700 milligrams of sodium. He wants to maximize protein in his breakfast meal. The first step is we need to define the variables. So, X will represent amount of cereal A in ounce and Y will represent the amount of cereal B in ounce. The second step is we need to determine the objective function, which is it already mentioned in the statement that Mr. Carter wants to maximize protein. So the objective function will be maximize Z equal to 9x plus 10y. The next step is identify the constraint. So in this case, we have two conditions that have been mentioned in the statement. First one is provide at least 480 calories and the second one is less than or equal to 700 milligrams of sodium. So the first constraint for calories requirement is 100x plus 140y more than or equal to 480 calories. And the second constraint for sodium amount is 150x plus 190y less than or equal to 700 milligrams of sodium. And we also have non-negativity constraint, which is x and y more than or equal to 0. So now we move to the important step, which is determine corner and intersection point. We find that when x equal to 0, substitute in the first constraint and solve it, we will get the value of x is 0 and y is 3.43. Then when we substitute y equal to 0 in the first constraint, we will get x equal to 4.8 and y equal to 0. The same steps we use in constraint 2, which is substitute x equal to 0, we will get x equal to 0 and y equal to 3.68. If substitute y equal to 0, we will have x equal to 4.67 and y equal to 0. So we need to solve in simultaneous equation to get the intersection point, which is constraint 1 represent equation 1 and constraint 2 will be represent equation 2. So equation 1 times 3, it will be 300x and 420y equal to 1440, we call as equation 3. And equation 2 times 2, so we will have 300x plus 380y equal to 1400, we call as equation 4. Final step in this simultaneous equation is equation 3 minus equation 4, then we will get y equal to 1. Then we need to substitute y equal to 1 in equation 1, we will get x equal to 3.4. For the next step, we choose point x equal to 3.43 and x equal to 3.68 because of that is the exact intercept from constraint equation when x equal to 0 into each equation. And we do not use value 4.8 and 4.67 because of it is not constraint line and do not satisfy the equation, so x is not feasible point. Then we need to substitute each point into z equal to 9x plus 10y. For point 0 and 3.43, z equal to 34.3. Next, for point 0 and 3.68, z will be equal to 36.98 and the last point is 3.4 and 1. Z will be equal to 40.6. So we could say that the maximum protein is 40.6 grams when x equal to 3.4 and y equal to 1. So that is all for my part. I will pass to the next presenter.
I will present a solution to a problem involving a juice stall at Bazar Ramadan Chandra, where the goal is to maximize revenue by deciding how many cups of two types of juice to produce, the refresher and the super duper. First, we define our variable. Let x1 represent the number of refresher produced and x2 represent the number of super duper produced. Next, we construct the objective function which represent total revenue. Each refresher is sold for 6 ringgit and each super duper is sold for 8 ringgit. So the total revenue is calculated as 6 times x1 plus 8 times x2. Our goal is to maximize this total revenue. Now, we form the constraint based on the available ingredients. For orange, each refresher use 3 orange and each super duper use 1 orange. Since there are only 50 orange available, the total number of orange used must not exceed 50. For apples, each refresher use 2 apples and each super duper use 3 apples. Since there are 40 apples available, the total apple usage must not exceed 40. For watermelon, only the super duper use watermelon and there are 10 slices available. So, the number of super duper produced cannot exceed 10. For ginger, only the refresher use ginger and there are 15 slices available. So, the number of refresher produced cannot exceed 15. Finally, both x1 and x2 must be 0 or positive since we cannot produce a negative number of drink. After forming all the constraints, we then analyze the problem using linear programming methods. This involves identify the visible region, which is the area that satisfies all the constraints such as limited orange, apples, watermelon, and ginger. Within this visible region, the maximal value of the objective function will always occur at one of the corner points, also known as the vertical. So, we evaluate this corner point by substituting their values into the objective function. After testing the possible corner points, we find that the optimal solution occurs at x1 equal to 5 and x2 equal to 10. This means producing 5 refresher and 10 super duper fully utilize the available resources without exceeding any constraint. Next, we substitute these values into the objective function to calculate the total revenue. So, we calculate 6 times 5 plus 8 times 10, which gives us 30 plus 80, resulting in a total of 110. Therefore, the maximum revenue that can be achieved is RM 110. In conclusion, to maximize profit, the stall owner should produce 5 refresher and 10 super duper, as this combination gives the highest possible revenue while still satisfying all resources limitation.
My name is Rabiatul Adawiyah binti Mat Jamil. My metric number is 30781. In today's presentation, I'm going to solve a practical linear programming problem focused on cost minimization. Meet Professor Simons. He needs to hire two graders, John, a graduate student, and Mary, a postdoctoral associate. John grades 20 papers per hour at a rate of $15, while Mary grades 30 papers per hour at a rate of $35. To justify their employment, each must work at least 1 hour per week with a minimum of 110 papers to grade weekly. How can Professor Simons distribute the workload to keep costs as low as possible? First, let's define our variables. X represent 2 hours John works and Y represent 2 hours Mary works. Since our goal is to minimize total cost, our objective function is min Z equals to 15x plus 25y. Next, we establish our constraints. Grading capacity is 20x plus 30y, bigger than 110 papers. Minimum hours, both x and y must be greater than or equal to 1. To visualize this, we simplify our grading constraint by dividing by 10, giving us 2x plus 3y equals to 11. When we calculate the intercept for the boundary line, if x is 0, y is approximately 3.67. If y is 0, x is 5.5. These points help us plot our feasible region on the graph. Because both employees must work at least 1 hour, we look for where this minimum hour constraint intersect our main gradient line. Setting John's work to the minimum of 1 hour equal to x equal to 1, we find Mary must work 3 hours to meet the paper quota. This gives us the point is 1, 3. Setting Mary's work to the minimum of 1 hour, which is y equals to 1, John must work 4 hours. This gives us the point 4, 1. Now we test these corner points in our cost function. At 1, 3, the cost is 15 multiple to 1 plus 25 multiple to 3, which equals to $90. Second, at 4, 1, the cost is 15 equal multiple to 4 plus 25 multiple to 1, which equals $85. The results are clear. To minimize cost, Professor Simons should employ John for 4 hours and Mary for 1 hour. This achieves a minimum weekly grading cost of $85.
I will present question 3, a linear programming problem, and show how to solve it using the syntax method. This problem is about a company producing 2 products, which is x1 and x2. The objective is to maximize profit. Z equals to 8x1 plus 2x2. There are 2 resource constraints. First, 4x1 plus 5x2 is less than or equal to 20. Second, 2x1 plus 6x2 is less than or equal to 18. This represents limited resource available for production. Also, x1 and x2 must be non-negativity. So, we will solve this linear programming problem using the simplest method. For this problem, we want to maximize the objective function z equals to 8x1 plus 2x2. Next, we want to convert all the constraints into equation by adding step variable. For the first constraint, we add x1 and become 4x1 plus 5x2 plus s1 equals to 20. For the second constraint, we add s2 become 2x1 plus 6x2 plus s2 equals to 18. All variable must be non-negativity. From the standard form, we construct the initial simplex tableau. The 0 is taken from the positive function, which is 8 for x1 and 2 for x2. The value in the x1 and x2 column come directly from the coefficient of the constraint. 4 and 5 from the first constraint and 2 and 6 from the second constraint. For the slack variable, they form an identity matrix. In the first row, which is the S1 row, the value in column S1 is 1 and in column S2 is 0. In the second row, which is the S2 row, the value in column S1 is 0 and in column S2 is 1. This is because each let variable only belongs to its own constraint. And then the Z row starts with zeros. Next, we calculate C minus Z. 8 minus 0 equals to 8 and 2 minus 0 equals to 2. Since 8 is the largest value, x1 is selected as the interior variable. And then the next step is we perform the ratio test to determine the leading variable. 20 divided by 4 equals to 5 and 18 divided by 2 equals to 9. The smallest value is 5, so S1 with the basis. Next, the pivot element is 4. Now, we divide the entire first row, which is S1 row, by 4. And the answer is 1, 5 over 4, 1 over 4, 0, and 5. This becomes the new x1 row. After that, we update the second row, which is S2 row. New S2 row equals to previous row minus 2 times new row of x1. The answer is 0, 7 over 2, negative 1 over 2, 1, and 8. The next step is we update the Z row. Z equals to previous Z plus 8 times new row of x1. The answer is 8, 10, 2, 0, and 40. Finally, we calculate C minus Z, and the answer is 0, negative 8, negative 2, and 0. In the final table, all values in the C minus Z row are 0 or negative. This means no further improvement is possible, so the solution is optimal. From the basis, x1 equals to 5 and x2 equals to 0. Finally, we calculate the maximum profit. Z equals 8 times 5 plus 2 times 0 equals 40. So the maximum profit is 40. For QM for Windows, I enter the same model as in the syntax method. The objective function is maximize Z equals to 8x1 plus 2x2. The constraints are constraint 1, 4x1 plus 5x2 is less than or equal to 20. Constraint 2, 2x1 plus 6x2 is less than or equal to 18. For the QM result, the optimal solution is x1 equals to 5 and x2 equals to 0 with a maximum value of Z equals to 40. This means only x1 is used to achieve the maximum profit. The result is consistent with the minor simple method calculation.
Assalamualaikum and hi, my name is Amni BINTI Kassim. My matrix number is 305578 and today I will be presenting question 4, which is a linear programming problem. This problem involves a company that produces two products, X1 and X2, using two assembly lines. Assembly line 1 has 100 available hours. Assembly line 2 has 42 available hours. The objective is to maximum profit given by Z equals 6x1 plus 4x2. Subject to constraints. First, 10x1 plus 10x2 less than or equal to 100. Second, 7x1 plus 3x2 less than or equal to 42. Lastly, x1, x2 greater than or equal to 0. To solve this problem, we use the simplex method, which helps us find the optimal solution step by step. After performing the simplex method, we obtain the optimal values of x1 and x2 that maximize profit. We also use QM for Windows software to verify the solution. The result from the software is consistent with the simplex method. Now, for step 1, we convert the constraints into standard form. We do this by adding select variables, which are S1 and S2, to change the inequalities into equations. So the equation becomes 10x1 plus 10x2 plus S1 equal 100, 7x1 plus 3x2 plus S2 equal 42. Next, we rewrite the objective function into Z form. So, Z minus 6x1 minus 4x2 equals 0. All variables x1, x2, s1 and s2 must be greater than or equal to 0. Finally, the initial solution is x1 equals 0, x2 equals 0, s1 equals 100, s2 equals 42, and z equals 0. This will be the starting point for solving the problem using the simplex method. So now this is initial simplex table. At the top, we have the coefficients of the objective function, which are 6 for x1 and 4 for x2. The basis variables are s1 and s2, since they are a part of the initial solution. The quantity column shows the available resources, which are 142. Next, we look at the C minus Z row, which help us determine the interim variable. From the table, the values are 6 for x1, 4 for x2. Since 6 is the largest positive value, x1 is chosen as the interim variable. Next, we calculate the ratio to find the leaving variable. For row S1, 100 divided 10 equals 10. For row S2, 42 divided 7 equal to 6. The smallest ratio is 6, so S2 is the leaving variable. Therefore, the pivot element is 7 at row S2, column S1. After performing all necessary row operations in iteration 1, we obtain table 2. In this new table, when we examine the C minus 0, we can see a positive value of 38 divided 7 located at the X2 column. Since we are solving a maximization problem, this positive value indicates that x2 is the entering variable. In other words, bringing x2 into the basis will help improve the objective function value. Next, we need to determine which variable will leave the basis. To do this, we perform the minimum ratio test. We divide the quantity column by the corresponding coefficient in the entering variable column for each row. For row S1, the calculation is 40 divided by 40 divided 7, which gives us a ratio of 7. For row X1, the calculation is 6 divided by 3 divided 7, which gives us a ratio of 40. The smallest ratio among these is 7, which belongs to row S1. Therefore, S1 is selected as the leaving variable. The pivot element for the next iteration is located at the intersection of row S1 and column X2, which is the value 40 divided 7. Next, this is tableau 3, which is final tableau. Now, we can see that all values in the C minus 0 are less than or equal to 0. Specifically, the value for S1 is 0, for X2 is 0, S1 is negative 1 over 4, and for S2 is negative 1 over 2. In a maximization problem, this condition, where all C minus 0 values are 0 or negative, indicates that no further improvement to the objective function is possible. Therefore, we have reached the optimal solution. Now, let us read the optimal solution from the table. Looking at the basis column, we can see that x1 and x2 are the basic variables. The quantity column shows that x1 equals 3 units and x2 equals 7 units. Finally, the objective function value z can be found at the bottom of the quantity column. The maximum profit or maximum value achieved is $46. In summary, the optimal production plan is to produce 3 units of product x1 and 7 units of product x2, which will yield a total maximum profit of $46. Lastly, to double check our manual syntax work, we solve the same problem using QM for Windows. The output confirms our problem setup. The QM solution gives us x1 equals 3 units and x2 equals 7 units with a maximum profit of $46, exactly what we found manually. Additionally, QM4 writes dual prices. For constraint 1, the dual prices is 2.5, meaning if we could increase that resource by 1 unit, profit will go up by $2.50. For constraint 2, the dual price is 5, which is even more valuable. This verification gives us confidence that our optimal solution is correct.